All right, we are live. Welcome, everyone.
How's everyone doing? I guess our sound and everything is good. We are so excited to have you all here. Let us know. I see so many people in the chat already. We are also super excited for this. Let us know in the chat, where are you talking from? What do you know about Ruby internals? What do you expect to learn from this session? And yeah, thanks everyone for being here.
Yeah, and we all need some tender love today.
Yeah,
Nice.
prepare yourselves. Lots of
Prepare
tender love
yourself.
today.
Tender love is in the building. He's going to join us in a second.
Yeah. Um, so let's get started.
Buenos dias, Pablo.
So many nice people. Some people that we already know, some people new.
Vancouver Island. Nice.
Yay.
Yay.
We are in Vancouver, by the way.
Wow. Welcome, Mercy.
From Kenya. Hi, Mercy.
People from New York. That's awesome. Thank you for coming.
I loved the avocado, by the way. Thomas.
Oh, I'm from India. It must be pretty late for you, so thank you so much for joining us. Hello
Wow.
from Argentina.
Oh, I see.
Denver and
Carolina.
Mexico. Wow. Lucas from Brazil, welcome. So many people. Awesome. Yeah, we are so happy to have you all with us today. I guess we can get started.
Yeah. We would just like to introduce us a little bit in case you don't know about hexdevs and open source Thursdays. So I guess we can share the slides.
Mm-hmm.
I am Stephanie and I love teaching and programming, more specifically with Ruby. And I am the co-founder of hexdevs.
I'm Thiago. I'm a software engineer and co-founder of hexdevs. And here at hexdevs, we help you become an expert developer. So if you're coming here today, we know that you have some skills that you want to learn, you want to level up in your career, and sometimes there's no job reason to learn some specific skills. For example, learning how a CPU works, learning how Ruby interacts with memory. How does that work, right? So it's not something that you do, that you use a lot, but it's important to know, because if you want to be a professional, those skills are very useful. And then what if you could learn those skills, so
From
that's
an
what,
expert.
from an expert. Yeah, so that's what we are doing here. We invite experts to join us to help us explain concepts so you can learn, you can practice. And then we have different types of programs to help developers improve in their career. Do you want to mention? So we have the open source Thursdays. We do every Thursday, and we are contributing to open source and showing people that it's possible. It's not a big deal. You don't have to be a genius to do it. And then we invite experts to help us. So today we have tenderlove, Aaron Patterson, who is an expert in Ruby and Ruby on Rails, which is pretty amazing. And then he's going to teach us everything about compilers and how to build a just-in-time compiler, which is super fascinating, right?
Yeah. So welcome again. And just to let you know, can you move the slides? Sorry, tremendous screen, so exciting. This event is possible. These expert sessions are possible because we are partnering up with Shopify. They have been helping us make these events bigger and free for everyone, because we share this mission on helping Ruby developers and helping the community in general. And so thank you, Shopify, for the partnership. And I think we have the agenda next. So just to let you know what you can expect for this session, we're going to talk a little bit about Ruby internals with TenderJIT. And Aaron is going to work on adding some missing features to TenderJIT. And then Shopify also gave us Three tickets?
Three tickets to RubyConf. So if you wanna join RubyConf, send your questions in the chat. We're gonna pick some questions that are interesting, and we're gonna ask Aaron. He's gonna answer. And yeah, you just made it. You made just in time, Thomas. And so ask your questions. We're gonna pick some questions, and we're gonna put your name on the list, and then we're gonna do a giveaway. So we have 3 tickets, and then after the session we do a Q&A, and yeah, so super exciting.
Yeah. All right. So I guess we can get started. You're all here for TenderLove. So Aaron, I hope you are ready. Only you could have made this. You know, you share your setup and then you became a meme. So welcome, Aaron. How is your day doing?
Hi. My day is going well, but I feel bad because you said you invited experts on this show and you got me.
Oh,
It's not true.
That's not true. Come on, we are all here.
I know. I'm kidding. I'll do my best to live up to that. Okay, how's that?
Yeah, just be you. We all know that.
At least you're a meme.
Yes. Yeah. I don't know. Like, I was setting up the streaming equipment. I'm like, I don't know how people do this regularly. This seems very hard.
It's true. It's really hard.
It's hard on the first few tries, but after a while it gets easier.
Yeah. All right. Well, so let me see. Oh, so sorry, Aaron. Go ahead.
Oh, nothing. It's okay. I'm like, I'm not sure where to put, like, I've got you all here. I'm like, you're on my second monitor, so when I'm looking at you, I'm like looking over here, but the camera's here, and I'm like,
No worries.
Yeah, no worries. So maybe, I don't know if we have already something from the chat, but just to get started, Aaron, I think the best way to get started would be, can you tell us the difference between an interpreter, a compiler, and a just-in-timer compiler? And then why TenderJIT?
Sorry, I should have given it a better name.
It's a nice name.
So an interpreter, well, it's kind of interesting because, like, an interpreter, well, let's see. How can I best compare and contrast these? It's kind of weird if you get into the details because, like, you have a compiler. The compiler will typically process the actual text of your code, and then turn that text into something else. Mm-hmm. So it's kind of weird to differentiate this because that text, like, it could convert it into machine code that runs assembly language, or it could convert it to, I don't know, some kind of intermediate representation, like a bytecode or something. For example, the Java compiler converts your code into a bytecode, or it could convert it into maybe just a tree shape, like a tree-shaped data structure. And when we talk about an interpreter, all it does is just takes these different instructions or whatever and interprets and runs them. So, for example, like in Ruby 1.8, it didn't have what you could think of as a compiler. It would turn your Ruby code into a tree type data structure and then interpret the tree, right? And in Ruby 1.9, we got a compiler. So Ruby 1.9 actually has a compiler inside of it, but it compiles your Ruby code into a bytecode. And then there's actually an interpreter that interprets that bytecode. And an interesting thing is, like, even if you were to write out machine code, your CPU is actually just interpreting the machine code. So it could be thought of as an interpreter as well. So it's kind of like, it's hard to say, like, where do we put that, like, make that definition exactly. What was the third thing? So interpreter, compiler, and
just-in-time compiler.
Just-in-time, yeah. So what just-in-time compiler, I think that's just talking about, like, when something happens. So just-in-time compilation is we want to just do that compilation step as late as possible, basically.
Nice. And then why TenderJIT then. I think that people are super curious about it. Like, is it?
Yeah.
Let's talk about the elephant in the room. Is it serious or is it just like
For fun.
for fun?
Actually, I have a presentation here that I can give about it. Should I do that now? Like,
Yeah.
okay.
Let's
All
do
right,
it.
cool. Yes. Okay. So I made like, we're gonna talk about it today, and I made a. Oh my God, no. Hold on. We want to play. We want to play in a window, please. Let's see.
Okay.
Play. I told you I'm not a pro at this.
No worries.
There we go.
Okay.
Am I on? Ah,
Yeah.
there we go. Okay. So I wanted to put together a few like slides about what, answer some questions. What is TenderJIT and how does it work so that we can start hacking on it today. And what it is it's a pure Ruby JIT compiler for Ruby. And I'm going to go through like why you asked what you asked me. We'll address that. I'm going to talk about different machine types and then what is a JIT, and then we're going to look at TenderJIT and some code too. So why the main reason I wrote this is at Shopify I'm on a team that's mostly a research team, and one of our current projects, one of the projects I'm working on is a JIT for Ruby, which is called YJIT, the letter Y, YJIT, not Y, the Y here. Let's hold on.
Great.
It works good. So I'm working on this JIT with the rest of my team, and to be honest, I don't feel very confident working on a JIT. I've never worked on a JIT before, and the JIT that we're writing at work is all written in C, and oh yes, so the slide is I'm not good at JITs. That's why I started writing this. So the way that I learn things is by actually implementing them. So I wanted to take the JIT that we had at work and to understand it better and to do more development work on it. I decided to say like, hey, can I implement my own, or can I do this? Can I do this myself? And the other reason I wanted to do it in Ruby is just to see if I could, just to see if it was possible. I mean, because I really love Ruby, and I think you asked this question: is this JIT real? And my answer is yes, it is. It is legit.
Legit.
Legit. But I think the question is is it really real? Like, is this a real JIT? Or is it just a learning project? And I think my answer is why not both? But seriously, if you want to compare this JIT to the one that we're working on at work, it's not. So this JIT is probably slower. Like the compilation times are probably slower, and maybe as we work on it, you'll start to understand why that is. And we can probably discuss it more in Q&A. And the other thing is, what is it? It's probably a little bit slower, but an interesting thing is that it should, theoretically, this JIT should be able to generate machine code that's just as good as any other JIT. So possibly the warm-up times for the JIT, or the amount of time that it takes to compile your code, could take a little bit longer. But the machine code that it comes up with when it's done compiling should be as good as any other JIT compiler out there. So your top speed, your maximum speed, should be about the same. Does anyone have any questions? If there's any questions, I'm happy to take them at any moment. I'm super happy if this is interactive or whatever, whatever folks want to do.
Right.
Sure.
So-
We have some questions on the chat.
Sure.
Let's see.
Yeah.
Yeah,
We
if
have one
if
that
you have
is.
questions, say, hey, Aaron.
Hey, Aaron. All right. So Adri is probably a little bit hard to find in the chat, but at Adri144N asked you what compiler books you found particularly useful. I don't know if you have any.
Well, it's kind of hard. It's kind of hard because a lot of the compiler books are very dense. I would say the Dragon book is helpful, and I've got a few other ones, but maybe I can give the list to you guys, and we can put it online somewhere.
Yeah,
Nice.
sure.
Because there's probably
Does that
no
sound okay?
compiler book written in Ruby, right? Most of them are either C or some other
C or
crazy
Java.
language.
But they the techniques generally apply to any language. What's interesting though is that the technique that one of the main techniques that we're going to use in this JIT, or that we're going to discuss today, is I think it's, I don't know if it's pioneered by or what, I'm not sure the total history of it, but one of my coworkers, she wrote her PhD thesis on this technique that we're going to use, and it's really cool. It's, once we get to it, you'll see it's quite an awesome technique. And unfortunately, I don't know of any books that of the compiler books I've seen, this technique isn't in any of them. So it's kind of hard to find good info.
You have to write it then.
Yeah. She should write it. I'm not gonna. I'm not writing a book. No, thank you. All right. So, any other questions, or should we keep going?
We have one from Lisa. So it's right. Actually, it's above that. Yes. So Lisa is asking, because Aaron, you are really famous for all your open source contributions, and
sure.
What would you answer to Lisa and to everyone?
How would someone get started? It depends. It depends on what you're interested in. So that's my, I don't know, kind of go-to answer when I get this question is, it depends on what you're interested in. If you're interested in doing web development, look at Rails, but start reading how things work. If you want to know how does link2 work, start reading the source code. And if you read it enough, you'll start to find edge cases, and you can fix those particular edge cases. As far as intimidation is concerned, I don't know. I'd say pick a friendly community. I think a Ruby community is particularly friendly. If you find stuff in Rails, people are super happy to help. Ruby's a little bit harder. I mean, people are friendly, but you got to do a lot of C code, which is not. I would agree that that's kind of intimidating.
Yeah.
For sure.
Yeah, that's why we have been doing the open source Thursdays. And it is still intimidating even after you spend some time.
But it gets better. Yeah, it gets easier.
Yeah.
If you stare at the code long enough, it'll get easier. Which we're gonna do. We're gonna do a lot of staring today.
Staring at each other.
Yeah, what is this? What does this code do? I have no idea. All right, let's take a look at. Let's talk about code execution and machine types, which I can't get my. There we go. So there's two types. There's two types of machines that we have to deal with. One is a stack-based machine, and one is a register-based machine. And I'm going to talk about how both of these machines work. Let's see. Oh, sorry. One sec. There we go. All right. So stack machines essentially just manipulate a stack. And I'm going to show you some examples here. So let's say we have this code here that's 5 plus 3. The compiler will convert this into machine code, but in this case it's stack manipulation instructions. What these instructions do is just manipulate a stack, and then it'll execute that code. So in this case, we'll convert 5 plus 3 into these 3 instructions, and the first instruction will just say push, and it'll push the number 5. and we keep what is called a machine stack, and it pushed that 5 onto the stack. So the next instruction says push 3, so it pushes the value 3 onto the stack. And then the third instruction is just the plus instruction, and what it's going to do is it's going to pop 2 values off of the stack, add them together, and then it's going to take the return value of that and push it back onto the stack. So we'll run plus, and it pops those 2, makes 8, and pushes that onto the machine stack. Now this is important. The reason we have to learn about this type of machine is because YARV, which is the virtual machine powering Ruby, is it's a stack-based machine. So that's how Ruby's virtual machine works. And if we have some code like this, like here's an example program, just the 5+3 example I showed earlier. If we check the instructions for it, so you can run this command ruby-dump insns, and it'll show you the instructions. You can see those instructions are almost exactly the same as what I showed in the previous slide. We have a put object. I'm not sure how. Oh no. We have a put object that pushes 5 on the stack, and then we push 3 onto the stack, and then we call opt plus, and that does the actual addition. So I want to cover a little bit of terminology here because this is going to be important when we start messing around with a JIT. This setup here, this particular arrow in the middle here that's pointing at the machine code, this is our program counter, or the PC. So when the machine executes, what it does is it increments the PC, it points it to the next instruction, and then it executes the current one. So the PC is typically pointing at the next thing that's going to execute. So we can imagine that this machine code is just an array of bytes or just a list of bytes, and it just points at the thing that's going to execute next. This other arrow over here is the SP, or the stack pointer. It's just a pointer that points at a list, and that list is just the values in your stack. And the way Ruby is set up, we always have like an empty one at the top, and we write into the empty one and then push down, basically. So our array can be indexed like this. We can have an instruction at place 0 or 1 or 2 or whatever, like the whole list, and then we have a machine stack with index 0 being the top value and -1 being the next one that we're going to write into. Some other important terminology is the CFP, or control frame pointer. This is something we have to deal with inside of a JIT. So what the control frame pointer is it's just a data structure that represents the current stack frame. Like whatever frame that we're executing in right now, that's CFP. So CFPs get pushed and popped as we call methods or return from methods. So for example, in this case, when we have foo here at the bottom, if we look at the CFP in this case, we have main at the top. Like if you ever do like put self inside a program, it'll say like main. So that's our top level stack frame. When we enter into foo here, we actually create a new stack frame, push it, and then we point to the previous one. And this keeps happening each time we call a function. So we'll push the new frame, and these frames are just called control frame pointers, or CFP is what you'll see throughout the code. And then when we return back, all these frames will get popped. So a few things like that are on the CFP that are important. Each control frame pointer has a few fields that are really important to us as JIT authors, and also for the virtual machine itself. One thing is the ISEQ, or instruction sequence, and that is representing the function that we're executing, or that thing that we're executing. So it could be a function or a block or a proc. That's what it's pointing at. The other thing that's stored on that frame is the program counter. So let's say we were to pause in the middle of execution. Like let's say we called in to add, and all of a sudden we froze the process and looked at it. If we did that, we would see that the PC is pointing at opt plus. So on the CFP or on the control frame, we're pointing at opt plus. And finally, the other important thing is the stack pointer is pointing at the top, and 3 and 5 are on that stack. So we have the PC at plus, and then the stack down here at the bottom, and the control frame pointer, the CFP, points to all of that information. And each of the control frames in that stack have their own PC and CFP. The other thing that's important is the execution context. And this is just like stuff. Being super descriptive here. This is just like stuff. But it's stuff that's specific to the virtual machine, and it's stuff that doesn't change. Importantly, it doesn't change as you push and pop frames. It's just like our main context for the VM. So the next thing I want to look at is register machines. And the reason we want to look at register machines is because, well, we're running like our PC is a register machine. Everything that we like, all these chips or any processors are going to be register machines. And a register machine, unlike a stack machine, basically it just has a bunch of registers, which are places to hold temporary values. So let's say we had this code again here. We have source code 5 plus 3. What we do is we have a bank of registers, and we can store values in each of the registers and ask the CPU to perform operations on those registers. So in this case, we would generate 3 instructions, and the MOV instruction, that just means write. Okay? And we're saying write the number 5 into the register called R1. So we'll execute that. And when we do that, the CPU puts 5 into that register. Then we'll execute the next one, the second instruction, it just puts 3 into the R2 register. Okay. And then the third instruction will say, hey, CPU, please add these 2 registers together. And it'll add the 2 registers and convert R1 to 8. So it'll do 5 plus 3, and it'll overwrite whatever value is in R1 with the 2 numbers added together. And an interesting thing is that, like, you'll notice I left 3 in the value slot. So it says like 3 right there. Yeah, that's on purpose. The CPU actually does that. It just leaves the value there. So it doesn't get cleared or anything. The value's just there. So I wanted to show you like the actual code. Oh, do we have any questions?
Yeah, we have some questions.
Sure.
Which one?
So we have, I'm trying to know which one is better now, but I think it looks like from the range of questions, people are really trying to understand what are the implications for the everyday use of Ruby, like, and how will it speed up?
Yeah, that's a really good question, and we're gonna get to that a little bit later in the slides. Mm-hmm. So this is, once we understand how these 2 machines work, we can combine them together in order to combine that knowledge in order to figure out how to actually speed up your programs. So mm-hmm. Can we pause on that question for a minute?
Yeah, for sure.
Okay, cool. Any other?
Good. I think I like the one from Randall. Like, how do you debug or benchmark a compiler?
We're also gonna do that.
Okay.
Nice. We are all
yes,
in the flow.
We're gonna do. Yep, we're gonna do both of these things. Once I get to the end of this presentation, we're gonna get into the terminal and actually do that.
Okay. So we have another interesting one from Jonathan.
Yes.
Is Ruby a compiled language? When would you use the JIT?
So the language is compiled, as in it's compiled into a bytecode, but it's not compiled into machine code. And we would use this JIT like basically the JIT would just work. Hopefully, I mean, ideally, what would happen is the JIT would work and you wouldn't know. It would just go. But you should use it like you would use it anytime you want your program to go faster. That's basically it.
That makes sense. Any other questions?
Okay, I think.
Yeah, there's an interesting one. How much of a difference will this make for Ruby in everyday use?
It depends on the load or the type of program. The JIT compiler that we've been working on at work, YJIT, we're seeing, I don't know, 3 to 4% speed improvements in production, and we're gonna make it faster. So like, I mean, it's not going to change anything in terms of the code that you actually write day to day, but whatever you write, that should just get faster.
Yeah, I saw the benchmarks. They are pretty interesting because I saw on the announcement where, for example, active record gets faster, and then you have some specific things that get faster, but then they run into some issues with the way that the interpreter was designed, because it wasn't meant to use a just-in-time compiler, right? So there are some things you need to change on the interpreter, I guess, to make it faster.
Yeah, that's true. The interpreter wasn't designed to have a JIT inside of it, so that's kind of a challenge that we've been having on our team. But I mean, part of our work now that actually we submitted YJIT to be merged into Ruby, and Matt's accepted it. So we're gonna have it merged in for the plan is to have it merged into the 3.1 release. But the really, really good news is that since our JIT is now blessed, it means that we can start working to refactor the internals of the interpreter to be more JIT friendly. So that's some of the more of the work that our team is going to be doing.
And that is pretty exciting. And I guess people here, they're interested in open source. So if they want to contribute, they will be able to, right?
Yeah, for sure. It's totally open source. Like TenderJIT is open source too. Look, you can contribute to my JIT as well.
Yours is cooler.
Well, so actually, the design of if C is somewhat, scary, you can get your feet wet by working on TenderJIT. The idea is the idea that I wanted to do is I wanted to make this very low. I wanted to make a JIT that's a really low barrier to entry, so you can start hacking on it right away. But the design is exactly the same as our production ready JIT. So once you get the feel for how the design works or how it's designed, then you can start contributing to the good one.
the official one.
Yes,
Nice.
The official one, the good one.
Yeah, we have one question. How do mJIT, YJIT, tenderJIT affect C extension usage in gems? Will it have an impact?
No impact. Should have no impact on them. That's one downside for all of these JITs, except with the big exception of Truffle Ruby, is that we can't see what the C extension is doing. And we're gonna as we work on TenderJIT, you'll see exactly why that is. But basically, if you call into a C function, the JIT can't understand what's going on inside of that C function. So we can optimize everything up to the call, but then after, once we get into that call, we can't do anything.
So, yeah, that makes sense.
If you have a tight, let's say you had a really tight loop that all it's doing is calling a C function, JIT's probably not going to do anything for you, unfortunately.
For sure. I think we can keep going.
All right. So I wanted to show like an example of a C program that's doing this example code, or doing this code, this 5+3. And I actually had like a really hard time making this because C compilers are pretty, I don't know, I can't get them to do what I want, basically. So we have this 5 and 3 here, and we say return 5 and 3. And this is the actual machine code that Clang generated for it. And it's kind of like weirdly inefficient, I think. We have, what's going on here is we say like, hey, we're going to copy 5 into memory. This is actually copying it into the stack. And then we're going to copy 3 into the stack. And then we're going to copy from the memory back into a register, like into a register. This is the register EAX. It's just a name. It's just called EAX. And then we're gonna do the add. Like it finally does the add right here. So we had to do this in 4 instructions, where, like you saw the example that I gave a little while ago did it in 3. All right. So what is a JIT? A JIT is just something that makes machine code at runtime. That's the way that I like to think about it. It's just something that makes machine code at runtime. So here is an example of some machine code at runtime. I wrote an assembler. So in order for us to actually like make a JIT, we need to be able to emit machine code, put together this machine code. So I wrote a gem that does that, and it is called Fisk. And in this example here, what we're doing is we're doing exactly the same thing, add 5 and 3. We just write 5 into the register RAX, and then we put 3 into R9, and then we add the 2, and then we return. And if we run this code, it'll just output 8. Okay? So our job as JIT authors is to just translate these YARV instructions into machine code. Or in other words, translate a stack machine into a register machine. Now, we had a really good question from the audience that I want to come back to and talk about right now, which is, how does this make anything faster? Like, how can this do anything? And I'll show you. I want to rewind in these, go back in these slides a little bit. Back to our interpreter right here. So each time YARV executes an instruction, executes one of its own instructions, has to increment this program counter. So it has machine code to increment the program counter. And then every time we push something onto the stack, it has to add that thing onto the stack and increment the SP pointer. So every one of these things, it's executing machine code to do those things all the time. So we essentially have a virtual machine that's sitting on top of a real machine. And the way that one very basic, extremely basic way that the JIT compiler can give us speed improvements is that we're eliminating that abstraction. So we know we can get rid of the abstraction and generate machine code for doing each of these things. And we can do some things like, for example, we don't need to increment the program counter every single time. We just execute the code. We don't do a PC. So the way you can think about this is the virtual machine has a program counter, but the CPU also has a program counter. And every time we're executing a YARV instruction, we're incrementing that abstract program counter from YARV, but we're also incrementing the CPU's program counter, and we don't need to do both. So eliminating that one thing is one way that the JIT compiler can save time for us. So with that, let's look at some actual code. I'm gonna move you over here. Actually, before we do any actual code, are there any more questions before we move?
I think people are so interested in everything and they want to keep the questions to the end.
Okay.
So we're keeping track of that.
All right. So just how about this? You interrupt me if there's a question you think we should talk about. Just interrupt me. Otherwise, I'm just gonna keep talking. All right. Let's see. All right. So the first thing I want to look at is is my font big enough? All right. There we go. So I want to look at. Let's see, presentation. Here we go. I want to look at this Fisk demo. So this is the code I was showing in the slides. Essentially, we're just moving value 5 into this register. We move value 3 into this register, then add the two values, and then we do a return. And we can very simply run this, define a method, and call it. And if we do that, so there we go, let's run it. Yay, we got 8. It's amazing. Just incredible.
Nice.
This is so the thing is since under my definition of JIT compiler makes machine code at runtime, we did it. We're done. This is a JIT compiler. We made machine code at runtime.
You just create the machine code yourself, right?
You just do it yourself. Yes, yeah. Exactly. So obviously this isn't what we really want to do. What I have here. This isn't what we really want to do. We wanted to convert our Ruby code into machine code. We don't want to write all this stuff, right? We want the Ruby code to just go there. So I want to try doing that right now. Let's try writing this. And actually I made it. We're just going to try doing this. So we'll do let's say we have this function foo and it's just going to return 5 plus 3. Oh, one other thing I wanted to mention here is since we're doing this assembly stuff ourselves, all of us know, when we're looking at this, that the result of this function is actually 8. So since we're doing this at runtime, we could just do this and then run that, and it's still 8.
Nice. That's easier.
Yeah, totally. So we know it's 3 plus 5. We know that that's 8, so we could just do that. All right. So back over here, let's take a look at this. We've got this function here, and we want to convert this. We want to convert this function into machine code. So we'll say Ruby VM instruction sequence of method foo. So this thing will give us the instruction sequences associated with this method. Actually, we could do puts. Let's output them. So we can do Ruby hello, and we'll see here are the instructions. We got put object op plus leave. So we got it. That's great. And we want to convert these into machine code. So let's require this, and we also need this. So we can convert this into an array. So we'll do we run this and print out what they are. What is it? Oh. Fine. What is that? Can't remember. Oh, helpers. All right. So if we print it out.
Live coding.
Yes. I'm sure everybody's yes. It's I told you I was afraid when you said you invited a professional.
Said
So-
expert.
Or expert. Okay, yeah.
Even more pressure.
Yes, I know. I feel the pressure. So if we call 2A on this, we'll see that it prints out a bunch of stuff, which like I don't really want to deal with. We're not going to deal with it right now because we just want to do kind of a demo that'll convert our code into machine code. Like it's got this stuff at the beginning that we don't care about. These, I mean, technically we care about all of it, but for the purposes of a demo, we do not. So let's get.
It's just stuff.
Yes, it's just stuff. Don't worry about it. If we look at the last thing in this array, we'll see we've got these like event things, which we're going to ignore. But you can see we've got here put object 5, put object 3, opt plus, and leave. And these are our like, this is the important stuff, the stuff we want to get to. So I'm going to do each, do INSN. And here we're going to do case INSN, and I'm going to use something that is new to me. We're going to do pattern matching on this. It's like pretty fancy.
Fancy.
Yeah, it's super fancy. So we care about these put objects. So we're going to look at put objects. Put object, and it's like some value v. PV. All right. I have no idea. Let's do this. I'm gonna be really awful.
Danilo is saying, I'm feeling smarter now. Thanks, Aaron.
What? Ah, oh! There we go. Oops.
Who needs else's?
There we go. We got that. Okay. So I was mentioning what our job is we need to convert the stack machine into a register machine. So what we'll do is in the compiler we're gonna have a fake stack. So we'll do like class stack, and this stack, all it's gonna do is it'll keep track of the number of items in the stack. So it'll keep track of how deep the stack is. So we'll just say like count 0, we'll do like def push, and it's just gonna like increment the stack, increment this value. Oops. So we'll do this, and that'll subtract 1. Okay. Now, we need to write the values out somewhere. So normally in the stack machine, it's written out to this stack, but we don't have a stack in a register machine. We have registers. So we want to write the values into registers, not into a stack. So we're going to keep track of the registers for x86, and this is specific to x86, though like the register names are specific to x86, and so are the instructions, but we could convert this to ARM too, or other processors. We're just going to do x86 today. So we'll do include, I want to include Fisk. Can you guys hear that? My cat is snoring.
That will be good.
Yes.
It's not the audience, it's just the cat.
Oh my god. Yeah, so she's right.
Oh.
She's also learning.
Yes.
The cat machine.
Yes, my cat snores very loudly. Okay. All right, so we'll include Fisk registers, and this gives us access to each register on x86. So we're gonna say like our registers we care about. We're just gonna say like we'll only use 2 registers today. We'll do R10 or R9 and R10. So this means that the deepest our stack can get is 2, which is, I mean, obviously that's not like good enough for real world code, but as a demo here. So what we'll do is when we push a value, how's this going to work? We'll push a value, but before we push, we're going to get the register. So we'll say reg equals registers at count, and then we'll return whatever that was. So when we first push, the return value of push is going to be R9. And when we pop, we're going to decrement, and then we'll just return whatever was there. So if it's 1 deep and we pop, then we'll get back R9. Okay. So we have a fake stack here, and this stack is helping us convert from a stack machine to a register machine. So now we'll say like, okay, let's create a new thing here, and we'll say like, actually, let me pull this. Should I pull this up a little bit? Yeah, okay. Pull this up, pull this over a little so I'm not in the way. All right. So we're gonna say like put objects. We want to push onto the stack in this case. Oh, we need a stack. So we'll say like, I don't know why Vim is not doing that correctly. We'll say stack dot push. Oh, come on, killing me. So now we know where to write. So we'll say, hey, Fisk, I want you to move reg to this register, and it's going to be an immediate value. Okay, like that. And now we have writes working. So every time we push, it'll write there. And actually, let's make a JIT buffer too, because we need to have a place to actually write this to. So Fisk will we can put together, like we can give it instructions. We can say, hey, here's all the instructions we want, but it doesn't actually assemble them until you say like write to this particular buffer. So you got to write it out somewhere. So we're gonna have a JIT buffer. We'll say Fisk, which I can't remember how to do. Actually, let's just look at my cheat sheet.
So there's a question about instruction sequence.
Yep. What is it?
So when you check the method using instruction sequence, is it using YARV already?
Is it using what already? Oh, YARV. Yeah. So this Ruby VM instruction sequence. Those are the YARV instructions. So it's like compiling it using YARV and giving you back the instructions that YARV would use. Actually, we can do. Let's do a little different example here. We could do like Ruby VM instruction sequence.compile. And then we can give it a string. Be like, I don't know, hello world. Let's do world with that. And then we can say like puts x.disasm. And then if we run it, there we go. We get the instructions back. So this is actually using YARV's compiler. So
Cool.
that's why as we were talking about it at the beginning, it's like hard to say where does the compile, like what does that mean exactly? Which I think it's funny, like I know a lot of people in the JavaScript community use the word like transpile, which just says like it's all compiling. You're just taking one thing and converting it to another. That's all it's doing.
Compilers all the way down.
Yeah, it is. Yes. Would or fix a typo in my silly demo. Anyway, yeah. So this is actually using the YARV compiler. Okay. So we got a JIT buffer here. This memory is executable. It allows us to actually run, like, memory in a computer has different flags on it, like your file system. So some files you have to like mark them as executable before you can run it. Memory has the same attributes. If you don't tag a bit of memory as executable, you can't actually run it. So this allocates some memory for us that is executable, and we can write to it. So we'll say here we'll do we'll do fisk dot write to JIT buff, and then it's not that interesting. Like if we just run this, it doesn't do anything. So let's like at least disassemble the code so we can see the machine code that we generated, which I'm totally gonna copy and paste for that because it's, I don't know, kind of long. I'm using this crabstone disassembler here. This thing will this will disassemble for us. So basically we tell crabstone, hey, we're using x86 64 and I want you to disassemble this memory. So I mean, don't worry about it too much, but we've only, oh yeah, we gotta require it too. So if we run this, yeah, this is neat. We're gonna switch Ruby versions. There's a bug in FFI with Ruby trunk. It's not actually a bug. So this is really kind of interesting. I tracked down what this is. The FFI gem uses finalizers, and if somebody raises an exception in a finalizer, it's just swallowed. But on Ruby 3, on trunk Ruby, it doesn't swallow the exception, it prints out the exception. So like there's all these exceptions happening all the time, and you don't know about it, but now we know about it. It's very noisy. So I'm gonna switch here. So let's do this again. Okay. There we go. So we ran it, and you can see here, here's our move to R9. We've written 5 into the R9 register, and we've written 3 into the R10 register. Okay. So we are able to translate these put objects into machine code. And then we have, what is the next instruction we have? Let's just, I guess let's look. We're not going to print this. I don't want to print this out every time. There's a trick I like to use. If you put end here, like everything below it becomes text, so I can just like comment that out. Okay, so we're not going to deal with to or Ruby line event, but we are going to do opt plus. So let's do opt plus. Now, in this case, I don't care what's here. We're going to assume a few things. First, we're going to assume that nobody's monkey patched plus. Second, we're going to assume we're only dealing with integers. Third, we're going to assume that it's not going to overflow. So I realize that's a lot of assumptions, but also we don't have like, I mean, our time is somewhat limited.
Yeah.
Right? All right. So how do we do this? Like we're in opt plus now, and remember the way that the stack machine works is we pop 2 values off, we add those 2 values, and then we push a value back on. So let's do that. So the left side is going to be, we have a left-hand side, we're just going to say equals stack.pop, okay? And our right-hand side is going to be stack.pop. And then we're going to say add. We're just going to use fisk.add. We're going to add a left, right, like that. And now we have to push a value back onto the stack. So we're going to say, okay, fisk.mov. So we want to write, and we're going to say stack.push. And remember, the value is going to end up in this left-hand side here. So the value that we added, our new value will be in the left-hand side in a register machine. So we're going to say, let's push the left-hand side onto the stack, or like this. All right, so if we run this, actually, let's go back here. We'll print this out. Okay, there we go. We've got our move, write the 5, write the 3, add the 2 values together, and then push the value onto the stack. So that did our add, but we've got one more instruction left before we can actually call this function, and that's if we run this, it's the leave instruction. This means we're leaving the method. So we got to return a value. So now remember, we did a push here. The put object, this pushed a value. Then we had a second one, so we did another push. So that's 2. Then we did an opt plus that popped 2 but added 1. So we have 1 value sitting on the stack. What we're going to do in the leave instruction is we're going to pop 1 value off of the stack. So as we leave, our stack is going to be size 0. We're going to pop the value off the stack, and that's the thing that we're going to return. So we'll say here leave. Oh. Now, I don't want to get too far into this, but the way the x86 calling convention works is when we return a value from a C function, it has to be placed into a particular register, which is the rax register. So what we'll do is we'll say fisc move. We want you to move into this register, just RAX. It's just the name of it. And we're going to pop off the stack. Like that. We're going to move into that register, and then we're also going to do a fisc.ret. So this says return. So we're done. I'm going to remove this. And if we print out the machine code, you can see here, okay, there's our 5, our 3, we add, we push, and then we're going to return whatever value was in R9. So that should be the value 8. And we can convert this into a function. Where did I do that before? Did that in here, fisc demo. So let's do that here. We'll convert it into a function and then call it. So we wrote it out. Oh my God, cat, come on. Okay. So we'll just call add. And there we go. We got the value 8. So yes, yay. Now, why, like, I mentioned this a little bit in the slides, but let's go back and talk about it again for a second. Why would this be any faster than the interpreter before? Well, remember, like, each of these pushes and pops, like we're doing a push here for each of these objects and a pop here for each of these instructions. We were able to eliminate all of those. When YARV is running, it actually has to run machine code to do that push and pop every single time. And now we're not even doing a push and a pop anymore. We're just writing into a register and manipulating the values in the register. Now, one other thing I want to point out here is if we take a look at this machine code, we'll actually see that it's got some, like, we can optimize this even better. We can optimize this even more. You'll see here, we've got this like add here. So we said like, we put a 5 in here, and we put a 3 in here, and then we added them together. So our number 8 is going to be in here in R10. And then we're putting 8, we're copying 8 into R9 again. So what we want is, we know at the end of this, we know at the end of add, at the end of opt plus, we want our value to be in R9, which is the right-hand side. That was, so we did 5 plus 3. Is that right? 5, stack, we push. I can't remember. Anyway, we want the value to end up in R9. So we're actually doing an extra move here. What we could do is we could say, well, instead of doing, do I have this backwards? We push 5, then push 3. Yeah, I totally have it backwards. This should be right. Actually, that'll flip it around for us. Great. So if we do this, we can eliminate this move. We'll just do stack.push so that we keep the stack in a consistent state. So we are virtually increasing the stack value, but not doing anything. So we're able to eliminate this move. If we run this, we still get 8. And if we print out the machine code, oops. If we print out the machine code, you can see, hey, we were able to eliminate this thing right here. So by doing tricks like this, we can speed up the machine code that we generate for some particular Ruby function.
That's really cool. So you can say one instruction.
Yes. And I mean, it's just one here, but you know, it adds up depending on the programs that you're dealing with, right? What else should we show here? One other thing that's kind of interesting is like this stack that we have is pretty fairly primitive. We don't know anything. All we know is we know the size. We know the size of the stack. But we could do certain things like here we know put object. We say like if we looked at put object, we can see what is v. Well, v is a 5 or a 3. We know it's an integer, so we could actually say like, hey, stack.push type v.class, for example. And then we can save that value here. So we'll say like, hey, type, what is a type? I'm not going to do it now, but we could keep track of that information. And then later on, when we pop off of this virtual stack, when we pop right here, we can say, hey, you know, what class was right? Or, you know, and we can say, hey, if right and left were strings, then we can do something specific to strings in the machine code. So we can use this virtual stack to start communicating information between each of the instructions. So this short program here is essentially how YJIT works, and it is also how TenderJIT works. How both of them work. How they convert machine code, or how they convert YARV bytecode into machine code. Any questions before we start poking at TenderJIT?
There's a question about the stack machine.
That one. Maple. Yes.
Can it be a mix of both a stack machine and a register-based machine? For example, you can manually specify which register in a stack-based VM.
Can it be a mix of both stack and register based? Can you manually specify which register in a stack-based VM? I mean, we kind of can. So that's kind of what we're doing here. Like we're specifying that the stack position 0 is at R9 or 1 is at R10. And that's like what we want to do, but I think conceptually, as we're messing with a different processor or like different machine, we want to have just one type, so that you know, like you can just think about one thing.
Yeah, that makes sense.
I hope that helps. Yeah, we have. So an interesting thing is that we have when we write to the stack in Ruby, so YARV. When it writes to the stack, it's actually writing into memory. It's not writing into registers. And that's actually a source of slowdowns. And interestingly, in YJIT, as well as TenderJIT, we're continuing to just write into memory. We're not actually writing into registers. So we'll write into memory, and then we'll move from memory into a register, and then do manipulations. So eventually, we would like to write a register allocator, so we do get that mix of stack/register. One other thing is, actually back to that question about stacks and registers. When we pass, should I get this deep into the weeds? Yeah, let's do it. Whatever.
Why not?
It's Thursday, right?
Almost Friday.
Yeah, it's almost Friday. It's basically Friday, right? So in C, when we call different functions, we have to have what's called a calling convention. So like, if you write a C function, you want to be able to call other C functions. And the problem is like the C function that you're calling, it doesn't know who is going to be calling it, right? So we had to come up with a way to say like, hey, I'm going to pass you function. I'm going to pass you some values. And we essentially came up like, I don't know who came up with it. Some people came up with a convention for calling functions. And essentially all that convention says is, okay, we're going to put parameter 0 in this one register, parameter 1 in this other register, 2, 3, 4, 5, etc. So we have a list of registers, and that's where we put all the parameters in. But like, there's only 6. So you can only do 6 in a register. So in that case, like, or you can only do 6 parameters, only pass 6 parameters via registers. After the 6th one, you actually have to start writing into the stack. So the C compiler will do that for you automatically. It knows like, okay, we're going to lay out all these parameters here. So in this case, we do have a mix of registers / stack, but it's, I mean, I don't know. We're going to try to kind of want to avoid that because I'm not that smart. All right, let's go look at TenderJIT now. So TenderJIT is on my GitHub. It's tenderlove / TenderJIT. And we're going to just go look at the code. And we're going to stash this because I was cheating and like trying to prepare stuff in advance so it would be less boring. So what we're going to do is we're going to run optcaret. Optcaret is a benchmark that we use for profiling Ruby or JITs. So this is how we do, like, this is how we start figuring out how fast the JIT is. It's a profiler we use for benchmarking that stuff. So I wanted to run that benchmark with my compiler and see how well it performs. So let's see. Here is the benchmark. There's a lot of stuff to run here, but basically we say like, hey, we're going to run this optcaret and the benchmark. Optcaret is an NES emulator for folks that don't know.
Wow, that's cool.
Yeah. So I had to modify this a little bit. TenderJIT has some limitations. And one of those limitations is that it doesn't automatically compile methods. I will make it automatically compile methods in the future. That's a very simple thing to do. I'm just doing manual compilation to make things easier to test. But if we look at, oh my gosh, you are really snoring, cat.
Yeah.
Stop it. Come on. Okay. So this is this is my patched optcaret. So basically I'm saying here we're going to create a new instance of TenderJIT, and we're going to pick out the run method, and we're going to compile the run method. And then we're going to manually enable the JIT, and then we're going to call run on the NES emulator. And down here, what TenderJIT does is it says, okay, for any instruction that we don't implement, we're essentially going to exit back to the interpreter. So we're going to exit back to YARV. So we're going to compile as many as we can, as many instructions as we can, and then run. And as soon as we hit an instruction that we can't deal with, we hand it back to the interpreter and let it continue execution. And here we keep track of, like, it keeps track of every time we exit, and we'll just print out the instructions that we're hitting and that we don't support yet. So the idea is like, we'll just run the benchmark, see what instructions we need to support, go implement the instruction, run the benchmark, etc. Like, basically repeat that process. Just keep running the benchmark, checking the instructions, implementing the instructions, and repeating until we get all of them implemented. So I have many of them implemented. Actually, not that many. Let's walk that back a little bit. I have some of them implemented.
Now you can just create a bunch of issues for one for each instruction.
So I was thinking of doing that, but then I was afraid it would be like a lot of spam. So there's if you check the repository in the test directory, actually let's look at the test directory. Ls test instructions. I have tests for every single instruction. And the ones that aren't supported yet, they just say like, let's do, what's one that's not supported yet? I don't know. Put string probably isn't supported. Yeah, it's just got a skip in there. It's like, please implement this, so you can like, if you want to help out with this, like go just find that and go implement the instruction. And we're gonna implement an instruction today, so you can see like how the process goes. And again, I want to like reiterate that this is essentially the same between TenderJIT and YJIT. So like, if you want to dive in and start messing with it in Ruby now, you can take that knowledge and directly transfer it over to YJIT and just implement instructions there as well. So if you want to work on something that's like production ready. Okay.
People are asking how many instructions are there.
That's a really great question. There are like 200. Actually, we can see now. Let's do Ruby VM. Let's do this with Ruby trunk. So if you haven't seen the new IRB, I highly recommend checking it out. It's awesome. Watch this. So I can say like Ruby, look at this. It like completes stuff.
Wow.
So like
that's amazing.
Yeah, it's awesome. I don't want any of those, but I want there we go. Instruction names. That's what I want. Does it tab complete? Oh my goodness, it tab completes. Look at that. So this lists all of the instructions, so we can count. Oh, jeez. This thing is very slick. I really like this. So there are 200 instructions. We don't have to actually we don't have to implement all of them. We only have to implement ones that are like popular or frequently used, right? So another interesting thing is these trace ones, these are actually generated instructions. So you may or may not be horrified to know this, but let's talk about trace point for a second. So let's say we do like, let's say we have this method foo, I don't know, do our normal like, do like AB. If you do trace point, so we know that this is going to be like, actually let's print it out here, ruby dump test.rb. So we have a few instructions, get local, so we're getting a one local, get another local, opt plus. It's very similar to the previous examples we saw, but these are just with locals because we're doing A and B here, right? If you do, like, I can't show this to you. It's not really possible. There's no way to print this out. But if you do trace point.new, I don't know, call something, and run it, we'll do like tp.enable, and you do like foo, whatever, disable, something like this. Ruby actually recompiles every single instruction sequence in your program in order to support this trace point. So it'll recompile all of these instructions, like the get local and the opt plus and all that jazz. So like when we look at, what was it, instruction name? Yeah, there we go. So if we look at these, all these ones that begin with trace underscore whatever, those are for supporting trace point. So maybe like, and there's one trace point instruction for every like regular instruction. So even though this said 200, we really only have 100 if we don't do trace points, which TenderJIT doesn't do. We don't do we don't support that. The huge team that is TenderJIT. All right. So let's look at opt_caret. Here we go. We're not going to compile it. Let's just run it without. Let's just run it. We'll just run it. Oh, hold on. Can I use trunk? Yeah, I can. Let's see. So we'll run it here. And when we run this, please stop snoring. Run this, we can see, oh, it's getting 35 frames per second. That seems pretty slow. I'm guessing OBS is like chewing up everything on here. So let's do with TenderJIT. Not gonna believe this. Yeah.
Yeah, that's better.
Nice. Slightly slower.
Why not?
Actually, I'm kind of proud of that. Like, it's not massively slower.
Yeah.
Could be worse, right? All right. So, one of the issues is we have, like, as I mentioned before, it's writing a compiler in Ruby. The compiler is probably going to be slower than C. But let's implement an instruction. So let's check out what's going on here. If we run this again, we can see what instructions we're exiting on. And the most popular, let's check the most popular. So the most popular, we exited on get constant once, we exited on newarray 25 times, and we exited on send 11 times. So we're going to start, like, this is our current target. So we'll start by implementing newarray. So let's do that. So all the instructions are implemented inside of this class, which is like very messy. If you would like to refactor something, that would be a good way to contribute to. The way this thing works is this class is responsible for compiling instruction sequence objects. So every method has an ISEQ, an instruction sequence associated with it, or ISEQ. Every block has an ISEQ, and this class is one-to-one with those ISEQs. So if we have a method like def_foo, this foo will get a compiler, an instance of the compiler, and so will bar. They'll both have their own instances of the compiler. And one thing about this compiler is that it is lazy. And this is where my colleague Maxime's research came in. It's a lazy compiler, and I'll show you in a minute. We'll get to it. But these ISEQ instances they exist for the life of the instruction sequence. So if we have def_foo again, it will have its own ISEQ compiler, and it will always have the same instance of an ISEQ compiler. So the compiler may pause for a bit and then re-enter at some point, and when it re-enters, it's the same instance. All right. Okay. Now we saw in the, I guess, yeah, we got tons of time. Let's just do this. Hopefully, if people aren't interested, then tell me you're not interested. We'll move on. We have to, when we do, let's find the compile method. So this is the main entry point. We instantiate a new instance and we say, hey, we're going to compile this. We keep track of the compiled method so we can see, like, we keep some stats. So we said, well, we're increasing one, we compile the method. And we resume compiling. So it has a method called resume compiling, and we tell where to resume compiling from, and we give the resume function a temp stack, like the stack that we were manipulating in the previous program. And since this is the first time we're being called, we resume at position 0. So we're resuming from the beginning. Now, if we look at resume compiling, this has to do some very interesting tricks to get the instruction sequences. So let me show an example. So we were using method. Let's do method foo. Actually, let's do. Yeah, that's fine. Fine. Let's say we get an instance variable. Oh, you know what? I don't need to write all this crap. I can just do like Ruby. Yeah, there we go. So we'll say get instance variable, and we see that the name of the instance variable is @foo, and you'll see this symbol here, which is very not descriptive. What this is, or what this is trying to say, is there is an inline cache here. It means that when this instruction gets executed, the virtual machine is going to check some values in here. This is going to point at some data structure, and it's going to check the values in there. And unfortunately, like we can't, like if we do .2a.last, let's do that, p. Oops. So if we run this, you can see there's just like some number here. It's just not a thing. Like we can't access that cache. So the JIT compiler needs to be able to access that cache. And that means we can't use this. We can't really use this API in order to get access to the instructions. I wrote a thing to get access to the instructions, which I will be talking about at RubyConf. I don't want to get into it here because it's like a ridiculous hack. It is just a ridiculous hack. But anyway, we can access all the instructions, get their name, their length, the parameters, including pointers to those caches, and handle them. And what we do is we say, okay, hey, do we implement a method named handle whatever, like handle some instruction? If we implement that, then we'll call that method, and that method will compile the instruction. So for example, we can say like handle nop, which is amazing. It's my favorite. The nop instruction does nothing, so we don't have to do anything. We're just done. Or handle dupe array copies an array. So it says like, hey, I need to copy this array. So it'll handle it. In this case, we were missing, what was it? Let's run this again. We were missing new array. So let's do that one. Do def handle new array. Now, what parameters does this method take? It has to take some parameters, and we're going to look at that. So in order to implement this method, we need to see how YARV implements this instruction. So let's do that. We'll do all instructions in YARV are defined in this file called insns.def. So if you go check out the Ruby repo and look at this file, you can see how instructions are defined. So we want to look for new array. So this has a description here, put new array initialized with num values on the stack. So this is the name of the instruction. This first thing here, that's a parameter for the instruction. This is the number of values it pops off of the stack, or what values it pops. And then this is what it pushes onto the stack. So since new array takes a variable number of, it can pop off a variable number of parameters, that's why there's 3 dots here. So I think we can actually see this instruction if we do, let's do 1. I think that'll do it. try that. No, that's a dupe array. Okay. So what this is we have an array that's stored inside the instructions, and we're going to dupe it. We're going to copy this and push it onto the stack. We want to do like new array. Let's try this. Yeah, there we go. So we push ourselves onto the stack. We call bar, and the receiver of bar is self. So self.bar, basically. And the return value of self.bar is pushed onto the stack. So we pop self and push the return value of bar. And then we say new array, and the length of the array is 1. And it's just going to use one value from the stack. We're going to pop one value off the stack. So back over here, now we know, hey, this num here corresponds to this one here. Or we could do like, let's do whatever. This should show us 3. Yeah, there we go. So it's going to pop three values off the stack. All right. So back over here, we know we're going to take num. So we'll do num here. Let's like print out num. P num. Actually, I should probably write a test for this. It's like, I'm not doing TDD. I didn't claim to be an expert.
Hey, Aaron,
Right, so
we have a quick question from Maida. Do we need knowledge of assembly in order to help the TenderJIT project?
So some assembly is required. It would be very helpful if you know some assembly, but if not, like, it's okay too. And I'm going to show you, I want to show off some of the things I'm working on in here. Like I'm actually really excited about this. I'm pushing Ruby DSLs to their very, very limit, and we're going to do that. So let's do like a new array. We'll write an array test. I'm going to show you the DSL. We'll see the DSL in here. So let's do like, I don't know, foo. What do we do? We need new array, but you can't use a literal because that doesn't work. It doesn't do what we want. Let's do like bar, and this is going to return 1. Let's do that. Do like bar. Okay. And then since I'm a really great programmer, I'm just going to copy paste from, let's say, I don't know, we got something in here? Yeah, sure, this seems good. All right, so we're going to compile the foo method. We'll call foo, and it doesn't take any parameters, but it's going to return to us an array. And the array should be what? It should be 1 like that, right? So we're going to compile foo. Foo is actually going to end up compiling bar. So we'll have 2 methods that get compiled. And we expect this to have 0 exits, so it's not going to exit back to the interpreter. And then we expect to have the return value of 3, like an array with 3 1s. So let's run that. Actually, I don't want to run with LDB. It's probably an easier way, a more bundle execu way to run this, but. So we'll run this. Wow. That's very wrong. Oh, right. This is because we didn't do anything. we essentially deleted all of the new array instructions because this didn't do anything. It just printed out num. So if we do like, if we do exit here, like we'll see num3. So let's see, let's run this. All right, there's our num3. Okay. All right. Yes. Do we have any questions? Do I need
So-
to? I need to move this.
Yeah, so Aaron, as much as we are all loving to see you code live, I think we are a bit past the time. I'm actually
okay.
sorry to say that
No.
the time has passed, but would you like to continue, or should we go to the questions now? We have lots of good questions in the chat. People have been waiting.
Let's do one more. Let's do like maybe 5 more minutes. I want to get to. So we had a question at the very beginning, which was like, how do you debug a JIT compiler? Which I kind of want to show that, and then I think let's call it a day. How's that?
Yeah, I mean, for me, we could go the entire day, but I know that sounds good.
Sounds
Okay.
good, yeah.
Okay, so what we're gonna do something very simple. We're just gonna call this function ec_array new from values. We're gonna do exactly the same thing that the interpreter does, and we'll do that by using a nice DSL that I wrote. I think it's nice. With runtime do RT. So we want to pass in the EC, this num, and then we need to pass in the stack values. So we're going to do that. We'll say rt.call cfunc, and we need to get the address of this C function. So we'll say address equals yes.
So Jeremy wants to keep going for another 3 hours.
Oh my god, no, I can't do that. Okay, so we're gonna get the address of the C function. So this is the address of the function, and we're gonna call it here. And we need to pass in 3 values, which is the EC. And I have kept those in a constant, so you can just say that I want to register the execution context. We talked about this. Then we need to pass in the num, and then we're gonna call like this stack adder from top. We have a temporary stack, so we need to use our temporary stack. So it's like temp stack dot peak num, and we want the location of that. So we're gonna do temp stack dot peak num location. Now, whatever this returns to us, we need to push that value onto the stack. So we're going to say, okay, let's do rt.push the return. We're going to push the return value. We're going to do that. And then we're going to do another thing here. We're going to do rt.push reg, which I'm not going to explain. It's a thing that I need to wrap up in the DSL. These 2 calls should be part of this. So if you want to do some contributions, you can just add these 2 calls to this method. Okay, so let's run this. Oh, I gotta give it a name. So we know it's gonna be, let's name this, oh no, sorry, here. Deleted too much. Name, it's an array. Because we know it's an array because we're doing new array. So we know the type here, so we can start passing the type around. So we'll say like type, I don't know, array. Feeling very excited here. Now if we run this, oh my god, killing me. Oh. So we'll run this, and then we see that it crashes.
Womp, womp, womp.
Yeah.
Thank you.
Okay. Okay, so one thing that's very exciting about working on a JIT is that it will segv, and this is what you have to deal with is this. So we have to debug this, and we're going to debug it here real quick and fix it, and then I think we'll quit. The way you debug it is you debug it with LLDB, and if we run this, run it, and we'll see that it's going to break. And it breaks right here. But honestly, like, this isn't very helpful, like, because we don't, I mean, I don't know, it's not super helpful. We see argc is 0, like, that's nice. It's good. And we see that this array thing here is 0, 8. And if we do a backtrace, so this is no fun. If you're working in a JIT, if you look at the backtrace, so you see, like, a lot of these addresses have a function associated with them. You see this one address here with no function associated with it. That is our JIT code. So that is the code that we generated. And see right here is our arbitrary new from values. And we can actually see that number 3. That's correct. That's what we wanted. But else here, so if we go to frame 2, else, this pointer is also 3, and that's not what we wanted. That is not a valid address. So what we can do is we can say, like, okay, rt.break. So we can add a breakpoint here. So we'll say let's do a breakpoint before we call this function. So we'll rerun this. This actually breaks inside of LLDB, and we can see, like, okay, here's the values. Here's 3 that we're passing in, ox3. We're using hex because this is hexdevs.
Yeah.
Oh boy. All right, so the issue is actually right here where we're reading from memory and we're dereferencing a pointer, and that's why we get this value 3 here. So we don't want to dereference a pointer. This function, RB, let's do LCD. This function actually wants a pointer to a value. It doesn't want the value, it wants a pointer. So we need to give it a pointer, and we're going to do that by saying rt.width ref temp stack, basically this guy here. And let's say we've got to delete this. Okay. Now we'll do this, and we're actually missing one other thing, which I'm gonna, since we're up on time, I'm just gonna do it. We're peeking at the stack to get that list of elements, because what's gonna happen here is we're gonna push. Remember, we're pushing 1, 1, 1 on the stack, and then we're gonna pop those 3 values off the stack and create an array. So this is reading from the stack. It's reading those 3 values, and now we need to pop those 3 values off the stack, because we're going to pop 3 and then push the array back on. So before we do this push right here, so we're doing a push here. Before we do the push, we're going to do num.times at temp stack.pop. So we'll pop whatever number of elements off the stack, and we'll push back onto the stack. Oops, not that guy. This guy. This is magic. All right, so we'll pop off the stack, then push back onto the stack. And if we run, let's get rid of the break here. Let's run it again. Did it work? No. Why? Let's see. Foo enable. Let's just run this. And now it's really crashing, and I don't know why.
Live coding.
Yes, it is very live coding. Let's do this. Let's look at my stash and see what I did, because I got it working. This works. Push, pop, type. Let's just copy. I have a great idea. Let's copy the one that I got working. and paste it here. What did I do differently? This looks... Oh. Y'all should have caught me here. Look at this. I did a push and then a push? No. These need to be matched up. It needs to be a pop. Wow. Wow. What did I break? Oh my gosh. Now you can see here that this is not working correctly. You can see from the number 1, some instance of whatever, and then false. Oh, maybe we should stop here. Num location. Yeah, let's stop here. I'm not sure what the problem is, and I'm quite scared of debugging it in front of an audience.
Disassembly and debugging stuff.
Yes. So
Yeah.
why don't we let's do some questions.
Sounds good. So yeah, I think we could all go for hours and hours, but Aaron, thank you so much.
Yes.
So
yes, thank you.
I think that some people are waiting for the giveaways. So I have the names of everyone. We'll just do the draw right now for the 3 winners, and then Aaron, you can rest a little bit, and then we'll go back to the questions.
All right, sounds good,
everyone. All right. So Mercy helped me with the names. Can you share my... Yes, that one.
All right, so let's do the giveaway. RubyConf 2021.
Good luck, everyone.
Let's spin the wheel.
Yeah. It's gonna be. Oh, yes. Yes. All right, so Mosley.
Sorry for mispronouncing your name.
Yeah. I will remove you from the list, so you already won.
Yeah, so you won. Let's see.
Congrats.
Congrats.
See you at RubyConf. Let's do the second winner. Drum roll.
Drum roll.
Yay, it's gonna be the second. Oh, Pierre. Marta Hell. Wow.
Congrats.
Okay. Congrats.
See you at RubyConf.
Thanks for participating, for asking questions, everyone. And now the last winner is going to be... Oh, I guess Lean
Hashiminov.
Yeah. All right.
Congrats. Yeah.
Congrats, everyone.
I'm gonna show the 3 winners.
Yeah. So I have it here, the results. So Mosen, Pierre, and Lean, please reach out to us either by email, team@hexdevs.com, or DM on Twitter.
And we'll send you your tickets to RubyConf. Congrats.
Yeah. And thanks everyone. Thanks to Shopify for the tickets. So now we will go to the section that we are all waiting for. We have lots of good questions. I think maybe we could get started with Julian. He was asking about the calls, if they are being done to the kernel or to the OS. Let me see if I can find the question. Yes. So Julian asked, does the compiler or the interpreter call those instructions directly from the kernel or through the OS?
I think you're on mute.
Aaron, you're... Okay.
On mute.
Sorry about that.
Okay.
It's not the same. It's not the same if somebody isn't isn't muted and talking, right? I'm not sure I totally understand the question. It's done. So I'll show you. I mean, we can go ahead and take a look. It's not. Oh shoot! I don't want a new Google window. Let's go over here. I can show you where it's being called exactly. Let's see. Maybe I can show you. So this function right here is the main. Oh shoot, let's do this so you can actually see my screen.
Yeah.
This is the main interpreter loop, VM exec, and the way that mjit works, and TenderJIT is just piggybacking off of mjit, is you'll see here like we say like the main interpreter loop calls this function mjit exec. And mjit exec, what it does is it keeps track of the total number of times a function's been called. And if it's been called enough, it compiles a function for that, or it compiles a method. And it sets that method on a function pointer here, this JIT func. So it generates machine code and sets it here. And then eventually down here, it calls it. So if there's no JIT function available, this function returns Q on def right here. You'll see it checks, is that Q on def? And if Q on def has been returned, then the interpreter takes it and runs it. So essentially it's just the interpreter is calling a function pointer. And TenderJIT is just hooking into that and sticking its own function pointer in there.
That's pretty cool.
Mm-hmm.
So for the next question, so Tian is asking, I'm curious to learn this during the Q&A. When you use tail call optimization, you need to structure your recursive function a certain way to optimize the function. What general tips should be followed to improve JIT compiling, specifically for tail call optimization?
Sure. Specifically for tail call optimization, I mean, just put all of your function calls at the end. If you're doing a recursive function call, do it at the end. Basically. But we're not doing, like right now, we're not doing anything like neither YJIT nor TenderJIT. None of the JITs for MRI are doing anything special with tail call optimizations. The main thing is like, what would make your code better for a JIT? I'm trying to think. Like, I hate this. This question makes me feel kind of weird because, like, from an implementer's perspective, somebody working on the virtual machine or working on the JIT, we don't want you to change your code. Like, we want you to write your code however you want to write it. Like, you do it. Like, you do you. And our job is to figure out how to make whatever you like to write faster. So, like, there's always this kind of like tension going back and forth. It's like, should I write this or should I write that? Like, should I write it so it's better for the interpreter or should I write it so it's better for me? Mm-hmm. And usually I would default to say, like, write it better for you. If you have something that's super performance critical, then maybe in that case, like, don't use splat args. Don't use keyword args are fine, but don't you use like star args or whatever. That stuff is hard to figure out. Specify all of your parameters. Do stuff that seems easy, basically. Yeah. If it's easy for you to understand, it's probably easy for the JIT to understand too. How's that rule of thumb?
Okay, that's a good point. Good strategy.
So it looks like Tim is saying that's not specifically, it's just an example of needing to write in a certain way.
Yeah. No, you shouldn't have to write anything. Don't write anything in a certain way. Just do whatever you want to do. Like, do what you like to do.
Nice. Okay. So I guess everyone, as much as we would love to ask all the questions, but Aaron has volunteered, I guess, to answer the questions on Twitter. Or even on TenderJIT.
Yeah. Please ask me questions anywhere. File an issue. Ask me questions on Twitter. Send me an email. Whatever. Like, do whatever. I'm really happy to, like, my goal with TenderJIT is to get you working into a JIT, and then the cat is get you working on a JIT, and then eventually get you into the production YJIT. Mm-hmm. Like the good. I keep saying the good one. Mine's good. Get you into the other one.
The other one sounds good. Yeah. So sorry everyone about that. Well, we don't know. Maybe a RubyConf Aaron will talk more, or maybe a part 2. We don't know. Stay tuned for that. So just to wrap up a little bit, we just wanted to say thanks to Aaron in the first place for being here, showing how it is to, make mistakes and debug things live. I think we all felt a bit normal seeing someone like Aaron also having to, oh, okay, what happened? So I hope that was a great session for everyone. And thank you, Aaron, so much.
Yeah, of course. Thank you so much for having me. I had a really fun time.
Yeah, I learned a lot, and it's always cool to hang out with people. I wish we could do this for like 10
Forever.
hours.
Yeah, I mean, yeah, our cats are also sleeping, so no problems. And also, thanks everyone. In the beginning, I was a little bit trying to make sense with all the questions and everything, but thanks for the feedback. And I also wanted to thank Shopify folks, Eamon, Mercy, Gabi, and Rafael. Rafael, by the way, I hope we lived up to the expectation to be legit.
It was a legit live stream.
And last but not least, thank you everyone who are here, shared the event, participated. We have other expert sessions with Shopify experts, and also we will have one with Chris Oliver from Go Rails. We are working on a workshop on just enough hotwire for Rails developers.
Yeah, so
stay tuned.
So we're gonna have Chris Oliver next month, right?
Yeah.
And we're also gonna do a giveaway of a Go Rails subscription. So stay tuned for that.
Yeah.
And because this is awesome. I love
it. We are super happy with all the support from the community. We hope this was a great session for you. And I think that was it. I hope you all are super happy just as we are.
Yeah.
And thanks again. Thank you, Aaron.
Thank you, Kat.
Yeah, I couldn't even keep up with the chat. I'm sorry, everyone. It was amazing. Thank you. See you on the next live. And it's always Friday somewhere, right, Aaron?
That's right. Yeah.
Yeah. So bye, everyone.
Thank you.
Bye.
See you.
I think